Okay, ladies and gentlemen, welcome back to the other video where we continue with our questions on Newton's laws of motion. So this is still particle dynamics, and now we're moving to problem 4, which is just saying find the constant force needed to accelerate a mass of 10,000 kg. Okay, so of a mass of 10,000 kg moving along a straight line from a speed of 54 kilometers per hour. Okay, so it's moving from a speed of 54 kilometers per hour to 108 kilometers per hour in 5 seconds. Now, assume the particle is moving in the positive direction of basis vector I. So that's the assumption we've been given. So it's moving to the right. This particle is moving to the right. Okay, so the solution is, of course, we know force is ma. Now, since we have a discrete problem, okay, what you have is not a continuous problem. It's discrete. Why is it discrete? Because we've been given the initial velocity and the final velocity. So given the initial and final in 5 seconds, we're required to find the um, the acceleration. Okay, so we can find the acceleration just by just saying v2 minus v1 over t. So this part in brackets is just acceleration. Okay, for a discrete problem. This is not continuous, it's discrete because we've been given the final, the initial and the final velocities, with the time it takes to achieve that. We use the formula for acceleration, which is v2 minus v1 over t. Okay, we use that just as we saw in the previous example. So you see this part in parentheses is v2 minus v1 over tau, the time, is the acceleration. So this is the acceleration multiplied by the mass gives the force. Something we're doing here. So we want to find the constant force needed to accelerate a mass of 10,000 kg moving along a straight line from this speed to that speed. That's what we want to find. So using the formula force equals ma. This is the same as Newton's second law. Force equals mass times acceleration. Acceleration in brackets. So the mass is 10,000. So this should be 10,000. So this is just 10,000. Okay, let's do that and put a 0 here. Okay, so that's another 0. This is 10,000. This is 10,000 kg multiplied by v2 here is the final velocity, which is 108 kilometers per hour, minus v1, which is 54 kilometers per hour, over time, which is 5 minutes. So now look what has happened. This is 10,000 kg coming back as it is. Now 108 minus 54 is just 54 kilometers per hour. You're getting that over 5 minutes. Now here, to get the answer in newtons, we must convert this 54 into meters per second, and this 5 minutes we must convert it in 2 seconds. So converting 54 into meters per second, this is the conversion happening here. So convert the kilometers and the hours. So conversion is easy. Just convert this 54 kilometers, convert it separately, and then convert the 1 hour separately, as I'm doing here. So I first converted the 54 kilometers, which is 54 kilometers, by multiplying it by 100 meters per kilometer. So that kilometer will cancel that. And this per hour, as you can see, is this over here, per. This over sign here is just this one here. Now, 1 hour, this is per hour, which is 1 hour. We're converting this 1 hour by multiplying it with 3,600 per hour. This is 3600 seconds per hour. The whole thing over. Now this 5 minutes. So 5 minutes times 60 seconds over 1 minute. So there are 60 seconds in a minute, so that's why I'm multiplying by 60. So taking all of this into your calculator, you find that you end up with 500 newtons as your final answer. So you can be explicit by saying 500 newtons in the I direction. So yeah, so this is 500 newtons I. And of course, this same answer here, you can go explicit by writing it in this form. That's if you want to show the direction as well, you can write it as 500. Okay, so yeah, I know using these pens can be a bit slow sometimes. 500 newtons I, and this is I hat, you see. This is with a hat. Um, okay, let's write it properly. Okay, so this is I with a hat. So we give it that, and this is I. You see, I with a hat, I hat. Okay, so this is a unit vector I hat, and you can put it in brackets and say 500 I newtons. So now that's been explicit, of course. So this expression is just something. This is that. So either you write it like that or like that, or I can still mark it. I can still mark it if you like it, if you write it like that. So this is just the explicit version of this. In here, even showing the direction, saying that it is pointing in the I direction. So you get that, you're okay. So moving on to the other question. Now this is resisting medium. So this part is talking about motion in a resisting medium. So number 5, this is question 5. We have a person on a bicycle, combined mass 80 kg. So this is the combined mass of the person with a bicycle, 80 kg, cycles along a horizontal road and produces a constant forward thrust of 200 newtons. So this is the forward force, the force which is making him go forward, 200 newtons against a variable force of resistance. So there is also a force of resistance resisting this man on the bicycle given by 4v squared newtons. Okay, where v is the person's speed in meters per second, and that the person starts from rest. So we're saying that this person starts from rest. Okay, it starts from rest. Find how fast they are traveling. Okay, okay. Find how fast they are traveling after 20 meters. Oh, that's the question. Want to find how fast they are traveling after 20 meters. So as you can see, there's a diagram here showing the direction of motion. You see the acceleration there is pointing to the right. So I mean that the direction of motion is towards the right. But look at the thrust is pointing also to the right by the arrow, 200 newtons to the right. And we've chosen right. We've chosen going to the right as positive. So if we choose right as positive, then left will be negative. So a coordinate system should always be chosen when you're solving problems. So you should choose right positive, left negative. Or should I say you should choose the direction of motion as positive. Okay, the direction of motion should be chosen positive. It's easier that way. Now, choosing right positive. Okay, as I have done. So, solution, the first thing you want to do is choose right positive, which is direction of motion. Now, since the data given involves V and S, this is V, mind you, and S, use A is equal to V dV over ds. This expression, we used it last time. We learned about this expression and where it comes from. So acceleration is just V dV over ds. S is just displacement. So since data given involves velocity and displacement, we use acceleration is equal to V dV over ds. Now we know that force is equal to ma. That is something we know. Force equals ma. Okay, so this means that force, which is the 200 newtons, is to the right, mean that it is positive. So the 200 newtons is positive, minus 4v squared. Okay, now the 4v squared is having a negative sign because it is going to the left. Look at where it is going. It is going opposite the positive direction. We've chosen right as positive, but this one is going to the left. That's why it's having a negative here. So 200 minus 4v squared is equal to ma. Now m, a, and a is just dv over ds times v, which is the same as me putting this v in front there. So I would have put this v somewhere here, but yeah, I think I just might have forgotten to put it first here. It should have been mv dv over ds, but even this is okay, it doesn't matter, this is the same thing. So now, moving on, 200 minus v squared is equal to mv dv over ds. Yes, now this is me putting it back in the position which is preferred. Now m is 80, which is 80 there, 80 kg v dv over ds, and we can divide both the left and right side, dividing it by 4. Dividing 200 by 4, we get that expression. Dividing 4v squared by 4, we get that. Dividing 80 by 4, we get 20v dv over ds. That's what you get. And from here, we can rearrange the terms such that the terms with ds, or the terms with s, variable s, they move on one side, and the terms with variable v, they move on one side as well. So this is just rearranging of variables. This is just integration. Okay, yeah, we'll just retry solving a differential equation here. So this is 20v over 50 minus v squared dv. This is when you rearrange the terms with v squared. We have that expression. Okay, so having this expression, we can integrate both sides now, so that the integral of the s is just s, and the limits, of course, we must put up the limits. Of course, displacement is running from 0 to 20. This object is starting from rest, so initially it is at 0 to 20, the position as we've been given. How fast they are traveling after 20 meters. Okay, so this object is starting from rest. Okay, so displacement is from 0 to 20, ds being equal to the integral from 0 to v, which we don't know since we're looking for the same v. So this is what we're putting from 0 to v of 20v over 50 minus v squared dv. Now, integral of the s is just s, and running from 0 to 20 equals the integral from 0 to v, 20v over 50 minus v squared dv. So we are having that there, and we really haven't even started any integration yet on the right side. We've only integrated the left side here. So now let us, or let's say let u equals 50 minus v squared. So we're letting this part in the denominator to be 50 minus v squared. So let u is equal to 50 minus v squared. Mean that du over dv is equal to minus 2v dv. So we're getting this expression just after differentiating this. And then afterwards, you make dv the subject. So from here, make dv the subject, you get du over negative 2v. So this dv will be substituted in there. Okay, you know integration by algebraic substitution. So this dv will be substituted in there, and we get this expression. And this denominator, we've made it to be u. This is what the u we're having here. And the 20v is maintained as it is there. So dv is just du over minus 2v. And we have that. So as you notice, the v will cancel with the v, and the 2 will divide into the 20, and we get negative 10. The 1 over u will come back with the du. Now here, the left side, we know that integrating here we had integrated the s, we found s, which is the displacement. Now substituting the upper minus the lower, we have this expression, lower to upper limit. So substituting this expression and subtracting, we have 20 minus 0. Here we have 20 minus 0 equals this minus 10 can come out of the integral, and we'll have minus 10. Integrating 1 over u with respect to u, we have the new with the limits running from 0 to v. So this object is starting from, of course, from rest, as we've been given in the question. So I mean that initial is 0 and some final is v, which we don't know, of course. So then you will substitute in this value for v and the 0 in there. Okay, but here we've been given that but u is equal to 50 minus v squared. So after getting to this point, you substitute for u back and you get that. Okay, with the limits as they are. So substituting for v, you're getting this expression, of course. I know there's v here and there's v here, but yeah, we're still getting the same thing there. Minus ln 50. So substituting for 0 in here, this part will just be 0 and we'll remain with ln 50. And the left side is, of course, 20 is equal to, okay, so now look here. This negative 10, okay, it's, of course, can stay outside. We can take, of course, this 10 outside, but we can multiply the negative. This negative can multiply inside there, and we can have this expression. So this negative multiplying by the negative ln 50, we'll have the positive ln 50 here, and this negative multiplying with this ln 50 minus v squared, we have a negative there, and that expression. But we have a natural logarithm, but we're subtracting the two, mean that we can divide these terms in parentheses. We can divide these terms in parentheses, and we can have 50 over 50 minus v squared, like that. So this whole expression is the same as this expression here. So from here we can have 20 equals 10 ln 50 over 50 minus v squared. We have that expression. Okay, so at this point we can now divide both the left and the right side. We can divide the left and the right by 10. You see there's a 10 here and there's a 20. They can divide to simplify. So if we say 10 into 10 and 10 into 20 here, 10 into 20 will just be 2, which is this 2. And 10 into 10 is just 1. And then after doing that, you might want to get rid of this natural logarithm, which is ln function. This ln function, to get rid of it, we must introduce an exponential on both sides. We must multiply by an exponential on both sides. So the left side, introducing an exponential here, will just be exponential 2, as it is here, exponential 2. And um, the right side introducing an exponential cancels with the ln function. So an exponential will cancel with this ln, and we'll just have a 50 over 50 minus v squared. We'll just have this term in parentheses. That's how they work. So here we're having exponential 2, and you're having exponential to the ln 50 over 50 minus v squared. This exponential cancels with this, and will just remain this thing dropping down like that. Okay. Now from here it is now easier to make v the subject of the formula. From here we can cross multiply to get this expression, and we can even make v squared the subject of the formula from here. As it is shown here, we can make v squared the subject of the formula. We get that expression v squared equals 50 minus 50 over exponential 2, which will get this here. Since exponential 2 is in the denominator, if we want it to be in line with this 50, we can add a negative to it like that, a negative power 2, which doesn't change anything. And this v squared, to get rid of the square, we can take square roots on both sides, left and right, square root, we get this expression. And of course the 50 has been factored out since it is common. We get that expression, which is this expression here. So this is the velocity. This is the velocity, which we can simplify further to v is equals 6.58 meters per second after traveling 20 meters. Okay, so we end here for the questions on particle dynamics. So we've looked at motion in a resistant medium and the ordinary problems of just applying the Newton's laws. So thank you very much, and see you in the next lesson.